Hi, everyone. Thank you for joining me this morning. Thank you for also having me. I feel honored to be here to speak to you about this topic. Thanks to Mark and Sarah for inviting me and helping with the arrangements. So the topic I'll be talking about today is on the prospects and challenges of machine learning for streets networks. And I'll try my best to carry, everyone along. Obviously, this is a virtual presentation, and it's much different than a physical one. So if you have questions, or if I have questions, and I know obviously everyone answers from you, you can leave your answers in the chat box. I can see them, and if you have questions, you can leave them in the chat box as well. I'll prefer the questions to be left for the end of the talk, and then we can deal with them in one go. Now, just for fun fact, on my slide, if anyone can recognizes the picture to the left or where that could represent, does anyone know where
Barcelona?
That is? Oh yeah, very correct. That's Barcelona, and I'd say that's like one of the most idyllic and picturesque cities for me in the world, and that's like the city blocks. On the right, I have the representation of the brain, which is supposed to depict artificial intelligence or machine learning in this case. And yeah, that's it for my fun fact. Hope that was a nice icebreaker. So move to the next slide. Cool. And a little about me. My name is Chidubem Iddianozie. Everyone calls me Chidi, and I'm a PhD student at the University College Dublin in the School of Computer Science, and I work with the Spatial Information Science Lab, and we do a lot of work on knowledge discovery for cities, for better urban living, critics and big data for cities, computer vision for slums, machine learning for street networks, which is me, and distributed processing for large spatial data, like LiDAR data. And prior to this, I studied at the University of Southampton, where I did my master's in computer science. And during that time, I interned at the Ordnance Survey in the UK, and I worked on the subgraph mining for the databases, which is the spatial database. It was developed in Neo4j, and I think that was when I realized I wanted to do stuff in the spatial space. Sounds very tautologic, but anyway, I realized that was what I wanted to do, because obviously I realized that work in this space has very far-reaching consequences to across boundaries, across different domains. And then just recently, I did intern with IBM Research as a research scientist for the machine learning lab, and also currently I'm interning with Huawei, the Ireland Research Center, and working on the knowledge graph construction team. And if you want to contact me, this is my email, and the handle on the bottom is my Twitter, as well as my Instagram as well. So the next slide, and then this presentation would be in 3 stages. I try to have it in 3 different sections so as to create cohesion. And at the very first beginning of this presentation, I'm going to talk about why anybody should care about machine learning for street networks. Why is it something that's worth talking about, or why is it something worth doing? And then I am going to discuss the work we've done in this space, and regards to results, proposals, challenges, and what we have done to mitigate those challenges. And then lastly, I'll conclude with reflections on our progress and what I think the future work should be. Obviously, at any point in time, if you feel like you have an idea, or you have a suggestion, or you have a question which I haven't addressed, you feel free to use the chat box to let me know about them. And I'm going to try as much as possible to have no, to leave no gaps, it is very likely that I'm going to leave gaps, that I'm going to like, forget to talk about certain stuff, important details. And please feel free to remind me, because yeah, that's a very big possibility that I'm going to like, skip important stuff and just assume prior knowledge of the audience. Yeah. And then the next, and now let's start. Why should anybody care about machine learning for street networks? Why, how does this affect you? Why should anybody want to even study these? And I'm of the opinion that this affects every one of us, because, these streets affect us. You're living close to one, you use one on a daily basis. And I also like to mention at this point that when we talk about street networks, we're talking about a type of spatial network. So when you think about general, maps where you have buildings and like, natural bodies like water or forest, the street network is a subset of this type of network. And I may use the words street networks and spatial network interchangeably, but for the most part, I mean street networks, just so you know. And one of the first reasons why I care about this and why you should care about this is because of the humanitarian efforts. And when we talk about humanitarian effort, we're talking about like things about immunization, disaster management, and even pandemic management, like COVID, for example. Because obviously, if governments and organizations do not know where you are, we can't really help you. We can't plan, effectively. If we don't know the state of the roads or the facilities that exist in the place, we don't know what what the people need, or what, how we may be able to reach them towards the need. And living, in the developed nation, we may take for granted how important maps are, especially when you think about, how easy it is for us to use things like Google Maps or Apple Maps to move from one place to the other. But at the very core of this, awesome service which we use, we need to understand that commercial maps are driven by the economic laws of supply and demand. So if a company was going to invest billions or trillions of dollars to map location, then it's assumed that they expect some sort of financial returns over time. And what this means is that there's certain places on Earth where they're not mapped yet, and this kind of very accurate mapping efforts hasn't reached them because for some reason they haven't been deemed profitable enough. And this has so many consequences, downstream consequences, because we have so many people who we don't know how to reach them, we don't know how to assess them, we don't know what they have on ground, we don't know how to help them if an occasion arises that we need to help them. But I will discuss this in a bit more detail in the consequent slides. And I just want to ask a very quick question. So there are, 7.8 billion people in the world. And how many people do you think I'm still missing from the world's maps today? Anyone can answer that in the chat, or nobody? Okay. Something. Oh, yeah. So now there are over 1 billion people missing from the world's maps. Like 1 billion out of 7.8 billion. That's wild. That's a lot of people. That's roughly 13% of the global population. And what this means is that people have no choice but to rely on collaborative mapping efforts like OpenStreetMap or the missing maps, which relies on volunteers who go out to map places. And then we see this people, like for example in the picture we have these two young people who are going out to map their cities, so to put them on the map. But then this kind of approaches, as much as they're very commendable, there are still limitations, and one of those limitations is the fact that someone being able to afford spending a whole day mapping, it's a privilege, because, people would, rather spend the time, going to work or going to study as opposed to spend the time volunteering. And then there's the issue of literacy, as well as who can afford or who is able to afford these high-end mapping devices. And others, as much as, collaborative mapping efforts are a way to curb the problem of missing people from the maps, it still needs to be sped up. It still has its challenges. Now, this also transcends to things like disaster management, because when we think about the fact that every year, over 100,000 people die from disasters, and over 200 million people are displaced. And then relief organizations, disaster management organizations have problems in giving help to these people, or replacing facilities that have been damaged because they are missing from the maps. So when you think about all this, like there's a missing map, people missing from the maps, and there's the issue of disaster management. It becomes really obvious how much of an impact or of a significance this problem is. And then when we talk about also, in line with the problem of people missing and not knowing what's on ground, government policies, even in the absence of any disaster, government policies are based off of what they think, is the problem or what's the situation on the ground. And if they don't have an idea of, who needs what, then the biggest, one of the biggest challenges that's going to, the biggest consequences that people who are going to suffer the most are usually the girl child, women, and and children who won't be able to either fight for themselves, and they will either be missed out of like opportunities like healthcare facilities or even or schools. And this all compounds the problem of people missing from the maps. But nonetheless, there's an opportunity for like machine learning and the use of AI to bridge this gap, to either add people to the maps, add the facilities, so we can know where they are, so we can know, what kind of, facilities exist for them. And one of those is the creation and updation of street geometries using machine learning. So in this case, we can say, for example, we can trace the pedestrian trajectories, and then we can use that to trace out the geometries of streets. Or we can, for example, we can look at the semantics of places, and then we can use data-driven models to either enrich or update this semantics. And these are like these are the opportunities that exist for machine learning to either to bridge this gap and be used in this space. Also, it's important to know that updation is a never-ending process. When I talk about updation, I mean the map updation. So, for example, it's one problem to actually have somebody on the map, but then, when I say somebody, I mean have spatial presence on the map. But then the process of updating the spatial states of a place is an ongoing process, is a never-ending process. And as much as as when changes happen, we need to update those as well. So even if so this is a problem that transcends even they're already missing people. It also affects established databases like, for example, Google Maps or Apple Maps. They need some way to either manually, automatically, to be able to reflect changes that occur on the ground. And now let's also talk about the effect of street layouts on quality of life. I think I'm going to quickly breeze through this because I seem to have gotten up to 15 minutes, and I plan for this talk to not go beyond 30 minutes. And I'll talk about the effect of street layouts on the quality of life. And then we see the way our streets are shaped, it affects who interacts with it, the resources we have access to, and how much we spend or save, as well as our mental health. So when we talk about street layouts and accessibility, we're talking about how easily is it for me to, for example, access healthcare, or access commercial services, or access entertainment, access education. Is it elderly friendly? Is it disabled friendly, and stuff like that? Also, we talk about street network sprawl, which is essentially the disconnected urban street networks. And this is highly correlated with increased travel time. And you see what I'm talking about in the next slide, where if you have disconnected street segment or street network segments or sub networks, then it means that you spend more time traveling between different components of the network, which in this case could be different sections of the city. So let's look at this map, for example, where we have two different cities and their and the route between two points in the city. For example, in London, we have point A is a source point, and B is a destination point. And essentially, the lines represent all the different routes we can take from A to B. And then we can easily see that there's kind of like a radial pattern, that shows here, which means that if I were to go from A to B, I would essentially have to go up to the edge of the city before I can find the connection to B. And then we look at New York City. It's not, I won't say it's similar because it's different as opposed to London that starts and that spreads out. I think it's quite easy for us. You can say it's quite easy you'd have many more options to go from A to B as opposed to A to B in London. So, this kind of characteristics and patterns lets you know that, how much the way the streets have shaped, how it affects us, how it affects our spending, our travel patterns, how it affects distribution and equality in places. And, it also, would affect like the mental health of people who live there, because the more time you spend, the more time you spend traveling, the less time you have to enjoy life. And, that's just an example. Now, an opportunity that presents itself here is, how come we can also predict the impact of urban layouts on social and economic, cultural sectors of a city. So we can say, oh, how much of a gap exists between the social strata of a place, or the economic strata of a place, or the cultural strata of a place, and then we can use that as a means to bridge gaps and make sure that we lessen the gap that exists between places. And then we can also determine factors that improve quality of life. So if people, are more prone to they like a scenic route to work, like if I'd rather walk to work as opposed to taking the tube, for example, those are things that people may enjoy doing as opposed to taking the bus every single day. So, issues like this could help us, improve the built environment, at least for the next generation. We can do this using things like AR and VR technologies and computer vision. And now I'll talk about some of the work we've done in this space. So generally, our goal is to be able to build maps and, and update them using machine learning models. And then, it's very easy to run into the temptation of being like, oh, well, you can build whole models. They can an end-to-end framework or whatever that can build and update and, but, it's a very ambitious goal, but I can tell you to the best of my knowledge, that's not essentially possible, at least with the data we have that's currently available. But however, an opportunity presents itself as a human in the loop system. So for example, you can have a human mapper who goes out to map streets. They can have, a model as a go-between that either validates or helps them map faster. So as opposed to, having to type in every single semantic themselves, you can suggest possible semantics using, for example, the contextual information of a place. And this also can help the system or the mapping system in terms of either speed or accuracy. So obviously, when we talk about the map as being not exactly literate or trained, then you realize that this could raise issues such as incorrect mapping. But having a model that assists in the way could help improve the accuracy of this mapping efforts, as well as increase the speed. And for this, for the purpose of this talk and purpose of this research endeavor, we use OpenStreetMap as a use case. And then, of course, we seek to evaluate how well these models perform across different dimensions, like accuracy will be one, speed as well will be one, generalizability will be one. But I know we discuss more details about this in the subsequent slides. Now, things to bear in mind. So these are like the challenges that we've realized that exist in terms, that impede us from achieving this goal, easily. But, I'll summarize them in this slide. Now, one of the biggest problems you come to realize is the data quality. And the data quality of this kind of, in this space is not essentially the best. So you have, there's a lack of good quality training data. There's extreme high class imbalance. The quality varies in terms of like, completeness and accuracy. So, when I mentioned about, different places, different parts of the world having different completion in terms of like of the maps. So it's, as much as we are, collaborative mapping is also it's a way to cope that problem, but still that's this same problem of missing people has also transcended in some way into this collaborative mapping effort, such that if you go to places in the global south, you'd have less accurate data. And when I talk about accuracy, I'm talking about in terms of like completeness and in terms of, how true the data is. So, if it's complete, that means, it's essentially complete. But if it's correct, then that means it reflects the true state of the data in real life. And then you have this disparity. So you may go to a place and realize that a place is labeled as a house, but in a sense it's not essentially a house. It may be, I don't know, a school, because of issues that are bound from non-trained professionals doing this. Now this problem now forces us, because obviously we want to be able to train models that can do create and update maps. It forces us to to get really creative about how we use this data. So we have to get really creative about that. And another problem that also exists is what? Representation. And what we say representation, we mean effective abstractions for data modeling. And then quickly, you can see that the native street network is seen as a graph. And the paradigm we employ would impose its own distributional assumption on this data. For example, if you were to go the way of traditional machine learning, that means, for example, that we have to assume independence for the data. But theoretically, street networks being spatial are bound by the first law of geography. And the first law of geography simply stating that everything is related, but to everything else, but near things are more related than distant things. And this forms the basis of theories like spatial dependence and autocorrelation. And so this is a problem that already exists. So when we think about it, some kind of like contradiction that exists between fields. Okay, if we were to like assume spatial dependence, but then we're using an independent paradigm. It suggests that we may not exactly get the best model. And another problem that also exists is a lack of benchmarks. And I mean standard data sets and models. So as much as we have everyone that tries to solve the problem in their own way, when we come together, everyone is doing it in a different way in terms of like they're using different data sets. They have a different scope of the data, a different model, different paradigm. So it's essentially hard to like to measure progress as well as performance. And then lastly, we'll talk about the ethical concerns, which is the trust and safety of these models and how well we can trust them. Let's nothing not be the case that we're trying to solve a problem using machine learning, and then at the end of the day, this solution ends up being weaponized against those who want to help with our models. And then our questions, I'm going to breeze through because it's 24 minutes. So I'm going to breeze through really quickly. So given the fact that I said, we'll have to get really creative with how we use our data. One of the ways we thought of using it was, okay, let's think about using transfer learning. Can we train models from, places with high quality data and then apply them to places where, the data is not so, not so good? Can we do that? Is it even possible? Is it, even if it's possible, can we improve on it? Can we devise ways to effectively leverage this knowledge? And then also we also talk about the representation. Since we already understand that the different assumptions that are in play or across this fields of study, how do we effectively model the data? How do we effectively collect features? How do we effectively model these features? And also, lastly, how do we improve the generalizability of these models? And the last question actually is well, I say it's a superset of the other questions, because to answer the last question, we need to effectively answer the other questions. But first, the really first question we need to answer is this even a transfer learning problem? Obviously, when you can just assume transfer learning is stupid for every situation, because necessary condition for transfer learning is that similarity exists between the domains and the question. So does it exist? That's the question. If it does, is it enough to allow for transfer learning? And then when we talk about street networks, it also begs the question: how do you measure the similarity between street networks such that if it exists, that it would reflect the possibility of the models being effective? And this formed the basis of one of our first papers that we sought to answer this question, and we developed a statistical multi-measure, which we used to a priori determine the suitable domains for transferability of the model. So, for example, we'll say, okay, we have a city and want to train a model on the city and then fine tune for downstream tasks. Is there a way to know beforehand that, or we have a set of models? Is there a way to know beforehand which would be the most suitable model for a particular target city? And but the big question in this instance is, how do you measure similarity for street networks? And then we had an idea to look at the similarity of street networks from the positional perspective of angular orientation for one. Obviously, we had multiple measures we were using to measure similarity, but this was one of them. And on the screen, you see this plot, which is essentially a polar plot, and this shows the angular orientation of the streets. And the angular plot is pretty much a circular histogram, and then we have the bins going from 0 to 360 degrees, and then the proportion of streets orientation that falls within a certain bin. It's essentially the length of the bars. And then we have it for 8 different cities, which we should consider in the very first our very first paper. And then in the first plot is for Chicago. You see that the street angles are essentially in four. It's pretty much clustered around 4 orientations, which is very depictive of the kind of streets you'd encounter in Chicago, for example, and San Francisco or Miami, or most modern North American cities where the streets are of a gridded nature. And then as we move to Europe, for example, Munich, we'll find that it becomes this behavior, it starts getting starts blurring out. And then Frankfurt is a bit more blurred out, and all the way to London and even Rome. I think Rome is probably the most blurred out. And then, but also we have an American city there, but obviously Charlotte is a very ancient American city in the sense that it was built way before the introduction of the motor car, which is the motivation for most gridded cities. And then this kind of a behavior is an example of the structural similarity that exists between cities, between domains, in terms of like how similar they are. And also you can think of this like as being the entropy, or the information that you can gather from the city's structure, the structural similarity. And we see that in the next slide, where if we compute the entropy for those cities, we see that the more gridded cities have very lesser entropy as opposed to the less gridded ones. And you can see from Chicago the value of entropy keeps on increasing as we get onto the most gridded, which in this case is Charlotte. And then in addition, we use this kind of measure of similarity as well as looking at the average length distribution, the probability distribution of the length as well, to determine how well a model for one city will be for another city based on how similar they are in terms of their features. And then I also like to mention this part that we're one of the first studies to, one of the first people to attempt undergoing this kind of large street network study for machine learning. And this, the motivation for this kind of large scale study was to, whatever results we're putting out there, that we have the confidence to say, yes, this has been tested and, on different real world data sets, and they seem to work. And then we showed the results for this endeavor. And obviously across the rows, we have the source domain. So for example, Chicago would be, get the pointer. This would be the source cities, and then on the left hand side you have the target. So this would be Chicago. Onto Chicago would be the same thing, and then we have Miami on Chicago, and so on and so forth. Actually, what you start seeing is that a pattern starts forming. The pattern is that the cities with a high entropy, that is Manchester, London, and Rome and Charlotte, seem to work better from a transfer learning perspective than the other cities. Like it kind of makes sense when you think about, from the point of view of entropy, it's probably, explains it. But when you look at it, in terms of like, in addition with the average length distribution, then, there's a pattern that seems to form, which is that, when you have cities that are less gridded, they might be better for cities that were more gridded. But anyway, the biggest takeaway from this was that transfer learning is actually possible, that this is a problem, this is an inadequate problem for transfer learning. This is not, we're not going to this blindly. And then the next thing we wanted to do was to, look at the use of contextual information. Obviously, while the first attempt was actually good in terms of like, we're able to like infer street types using very minimal features, but then it's focused immediately on transfer learning. Well, another thing we wanted to see was, could we inform could we build models using contextual information? And when I talk about contextual information, I'm talking about like when you have a street segment, you look at the type of object that exists within the vicinity of that street segment, and see if it could help you build a model that would be able to infer that object correctly. For example, let's think of something like a residential street. If you would assume that a residential street would be in the vicinity of other residential buildings as opposed to close to a factory. And what this means, what this essentially means is that if you were to put this in, represent this, as data as a feature metrics or whatever, then the model would, most likely to infer the type of an object correctly. But then we went ahead to do this using the multiple fixed buffer approach. And what that means is we overlaid buffers over multiple buffers over a street segment, and then we collected this contextual information for each of these buffers, and then what we represented each contextual information as a function of the distance of the buffer. In this instance, the buffers of different radiuses and of different distances from a particular street segment. So then would represent the count of this object as a function of the distance from the segments in questions. But obviously, there's another problem that that we could run into this. There could be a very large number of contextual information that exists within a particular distance from a street. So when you think about it from the point of view of transfer learning, you could say quickly that what if this data doesn't exist in another city? What if we were trying to use this for another city and then we can't find it there, or it doesn't exist there, or it's not available there, or it's incorrect there? Like, is there any way we could like reduce the scope and the size of these features? And then we quickly realized that this was a budget problem, and then we modeled this as a budget problem, and then we said, okay, let's try to see if we could learn on a budget for this using this contextual information. And I will propose to do this using urban function. Urban functions simply describe the use of a location. And then our major hypothesis was certain urban functions are correlated with certain street types and maybe better for inference when when we're on a budget. And we're trying to dispose or accept this this hypothesis. And then we formulated four different urban functions. For example, we had recreational, utilities, residential, and commercial urban functions. So for recreational, you could say objects that will fall as being recreational would be, for example, things like cinemas, things like pubs, things like bars, things like hotels, things like restaurants would fall under recreational urban function. And then we classed each of these type of features into different let's say definitions, and try to see if there was any direct correlation. And then we found that there was no direct correlation between the urban functions, any of the urban functions which we used, and street types. Rather, there were certain urban functions that were better predictors than the others, that they were better overall, better for all street types than the other types of urban functions. And that was a good second attempt. But then we also thought about, okay, how do we improve the representation? Obviously, we were making different assumptions, and what if our model could be improved in terms of like representations we're using? Since right now we're training away the dependence that exists between, or the relational dependence that exists between street segments. And then we thought about using graph neural networks for street networks. And for those of us that notice or don't really work with this. So graph neural nets are essentially neural networks that work on graph or for unstructured data generally, but are specifically designed for graphs, which is a type of unstructured network. And you could either do this using message passing or aggregation. Like for example, for the node classification case, if we look at a node, the red node, so we'll represent the red node as a function of its neighbors. Now, the neighbors are essentially the one-hop neighbors from the red node, which is essentially the neighborhood of that particular node. And this is essentially done for every other node within the graph, which you want to use for the training. And also, I have to beg your indulgence. The other results I'm going to speak about from here on out are still under review. So I'd really appreciate if I beg your discretion. But anyway, the real idea, the real reason why this was interesting to us was the fact that node sharing between message passing between nodes sounds like something which would would beneficial to the entire learning process for spatial networks. And then we proceeded to attribute street networks or represent street networks as graphs. And then, sorry, was that a message? Oh. Sorry, can you hear me? I'm not just talking.
Yes, it's all good.
Okay, cool. So one of the first things we had to do was to represent the street networks as graphs, and we had to do it using, we had to represent the street networks as attributed graphs. Specifically, we had to represent the street networks as homogeneous, multi-class, undirected, attributed graphs. And then we essentially take a street network, and then the node of the street network would be the node itself, it would be the street itself, and that the edges between streets segments would denote intersection between street segments. And each of the streets are labeled. For example, the street type, the speed limit, the number of lanes that exist in the particular streets, and then we also attribute a particular node using the contextual information which we talked about before. However, when we thought about the implementation of graph neural nets for spatial street networks, there are a few things which we realized were quite different in terms of like assumptions. And one of those was the focus on local structure. Now, the thing with graph neural network is that most of the popular implementations focus on a local information passing. So when we talk about When we talk about, for example, when we look at this, so when we do message passing, for example, at this level of the local structure of this node, this is how most graph neural nets usually work. And they throw away or they ignore the global structure, the global characteristic of this particular graph. And that was something we realized that would this really be good for our case? And obviously this would, this ties into the fact that our graphs are very, very imbalanced. And what I mean very imbalanced, I mean very imbalanced. I'm going to show details about this in later slides, such that you can have maybe up to order of magnitude 10 in terms of difference between the sizes of the class sizes of two different street types. And we thought about saying, okay, if this local structure is the only thing we're considering here, then we may run into problems such that we would miss out we'll not have enough data to train certain classes. And then this also ties into the assumptions of GNNs, which is homophily. And the implementing GNNs using local structure is dependent on the assumption that that a node class is is related to every other node class close to it. It thinks about local structures being a cluster of nodes of the same type, whereas this is not essentially the case. For example, in street networks, you find out that the density of street networks is maybe between 2 and 4, but no more than that. And then this makes sense because when you think about like the intersection of road networks, you can see to a very large extent that with high confidence that you wouldn't find a street with more than 5 degrees, like maybe 90% or 95% of the street networks in the world have less than 5 degrees. In this case, we're talking about a 4-way junction. But then, this is not exactly the case for different other kind of like networks, like citation networks or social networks. For example, the mean degree of a social network is 9.15, whereas the one of a social network is 492. So this kind of like very, very high disparity in terms of density. Now, we talk about this as graph density. Would suggest that if we went into implementing graph neural nets for street network blindly, we may run into problems. And then we say, okay, is there any way we could actually improve on what we have on the current implementations in terms of either maybe sampling more important nodes for a highly imbalanced network, or is there a way to I don't know is there a way to model the representations better? These are the questions that we had in mind. We're like, okay, let's actually try to devise a way to do this better. And then this is an example of the class imbalance that exists for nine street types across 3 cities. And then you find this is represented as a proportion of each other, and it's the log scale. And you find that there's some sort of like power law distribution going on here. But the key takeaway, the key thing I want to take away is the fact that when you think about, for example, we talk about primary link and residential, you find this high disparity between the main the majority class is residential and primary link. And then you find that this structure is very, very it's shared across all the different city types which are constrained in this case. And I go to the next slide. And then we talked about, okay, let's see how we can represent node importance in such a way that in multi-class structures that are imbalanced, we'll be able to still model or be able to train for classes that that are not well represented, or for sparse graphs such as street networks. And let's look at this the two figures on the screen. On the left-hand side, we have a single class structure where you have a green node, which is of the same class as the same, as other nodes. And in this particular instance, we could say that the green node is of a high importance in that particular structure. And then we'll talk about a multi-class structure, like on the right-hand side, where the green node could be a member of either classes, either the right-hand side or the left-hand side. but then it would seem that you could say that that particular node on the right-hand side would be more important than any other node in any of the classes. So if we assume that this kind of structure exists in our street networks, which is a multi-class, highly imbalanced graph structure, then we could say we can pick certain nodes that are very important and use those nodes, and they would, we could train better models than on average. And but essentially the idea was to be able to have nodes that don't just represent the classes well, but are able to discriminate their classes against other classes. So classes that are both globally important as well as locally important. And that was in the paper which we have in the review at the moment, we proposed the way to be able to sample this nodes for training, especially for for highly imbalanced cases. And then we'll talk about I want to show you the training and validation accuracies for this for model as opposed to survey ad model, which is GAT. Obviously, we did this for every other, like GCN and GraphSage, but just for brevity, I'm just going to show you for the one for GAT, because GAT seems to be the only one that works, even without any kind of tweaking. It works, really well for our case. And on the left hand side, we have the training accuracy, and on the top, this row is for GAT, and this row is ours. And we see that the GATS architecture quickly overfits the data, like in less than 10 epochs, as opposed to ours, which there seems to be a gradual progression. But that's not even the biggest takeaway. For me, I think the biggest takeaway is in terms of like how generalizable and how much of an affinity. So we see the effect of this here, where we see that when we test the model trained on a validation set, it's not as good as, for example, when we train it when we sample the nodes using some kind of like importance measure. We see here that the performance, works really well, and the progression with the training on the training model correlates with the validation accuracy. Now, because we were trying to model not just against a balanced case, we also wanted to see how well our models, performed, on an imbalanced case. We devised a way to sample nodes at the balance scale, and then sample them as a proportion of the class size. And we used the micro F1 score for the first instance to show the results for the balance case, and then use a macro F1 score, which penalizes for majority classes, to penalize for to show for the proportionate case. I'm going to rush through this. This is simply a proportion showing how well the model, how much of an improvement the model gives as opposed to the general case. And we can see that on average, we need at least 8 attention heads or more to ensure stability, to have the negative kind of performance. I'm going to rush through this, I'm sorry. And then something else we wanted to do was to be able to learn from multiple cities. Now we've established the transfer learning works. We've established that contextual information is good. We've established that GNNs also work, although with some form of tweaking the work for it. But I also want to extend it to such a way that we would be able to learn from multiple cities, exploit this knowledge that we get from multiple domains. Or so in this instance, we can regard the domain as a city, as a country, as a town, as a village. It depends on the problem you're trying to solve. But in this case, we refer to domains as cities. So how can we learn effectively from multiple cities to attribute or infer for a particular target city? And obviously, we don't want to run into the problem of negative transfer. We don't want to run into, because negative transfer is something usually discovered that usually occurs when we do naive transfer learning. So the big question here was, how do we take this knowledge learned from different cities and then merge them together and then learn for one particular city? And then we propose to do this using using class-wise graph similarity, and then without using kind of the similarity between classes of a graph. And then we use model assembly techniques. Again, I said the results, the method and the results and the description of the experiment are currently under review. So I'm going to say that much and then talk about the results. But if you have any questions regarding this, please feel free to ask me, in the chat or after the presentation. And then these are the results of that approach. Now here, this SAT is our framework, and these are the results across different data sets. And then we have the GCN, GAT, and GraphSage compared against our framework. And one of the things for our frameworks, we use different. We propose another sampling technique, and we had it as S1 as S2, and then we use random sampling, which in this case is the one without either S, is just SAT. And then we took the best results for GCN and GAT and GraphSage, and we'll present it here as well. And we can see clearly that our results, our framework seems to work, really good for many of the cases. And then we also try to see how much of an improvement, in attempt to see how well or how easily it is to fall into a trap of negative transfer. And then we try to see how well, how much of an improvement occurs from using knowledge learned from other cities as opposed to using the parent models. And then for GCNs and the other sort of the arts methods, we see that negative transfer occurs in many cases, but then for us across board, we do not encounter any kind of negative transfer. As a matter of fact, we see consistent improvements in terms of model performance across board. And yeah. And then let's quickly talk about, I'm going to quickly talk about the reflections and the frame and the future work. And one of the big things that we've realized is that the data is inherently, low quality. It's sparse. It's not consistent, and it forces you to really think, be clever about the way you go about creating models to either create or update maps. And then we've considered transfer learning as one of those approaches, but then there are other ways we could also think about or implement in future work. For example, things like future learning, for example, could be a way to go about it. And semantic heterogeneity, which is something where, different languages, different places call things differently. For example, bars in the US could be referred to as pubs here. And then, you have this kind of, semantic heterogeneity that exists across different domains. And, we need to be able to ensure that our models are able to, solve for that and not, be swayed, in some kind of adversarial way and not be able to, handle issues like that. And there's a lightly resource field. That means it ties back with the thing I said before about, you have to get really clever. And representational approaches are still developing. So, as much as we're trying to see if dependence is a relational dependence is something that could actually improve model performance or not, approaches are still developing. So as much as we've made some progress, I still feel like, we're still at the very early stages, and then, there's still a lot of work to be done. So, and then there's another, there's an extension that we could actually, veer into, and that's something we're currently, doing right now, which is heterogeneous spatial graphs. So as much as we've talked about street networks, the street networks do not exist in a vacuum. We also have houses, for example, or buildings, and we also have things like natural bodies, like forests, natural parks, and we could present all these entities in some kind of heterogeneous spatial graph. As a matter of fact, I'm of the opinion that if we want to, if we want to move, like this is the true nature of representation for this kind of graphs, because these entities do not exist in a vacuum. They relate to each other with different different relations. For example, you can say if this is a primary street, you can intersect with another street. It can be encoded as being close to another, I don't know, building or cinema, and then we can say this, for example, is within a particular distance of a lake. We can encode all these entities together, as well as the heterogeneity, using different types of edges as well as different type of nodes. And I think that is the nature of third and next step for us to see how well graph newness for one can be extended into this kind of representation. But obviously, one of the big problems with this kind of representations as they relate to real life data is that it is tricky to present objects with this across different relational types. And creating the data set for one is even a big step. But I just want to talk about, I just want to say that this is what I think is, it's going to be a really interesting direction to play into. And this is related to that, but I'm not going to talk about it because time is no longer on my side. And then multimodal learning is something as well that we could explore, which is the use of both raster data, aerial images, satellite imagery, as well as regular street networks, which are not raster data, essentially geometries. You imagine two of them together could lead us into could lead better results. And then back to the issue of standard benchmarks. The lack of a standard benchmark leads to problems where people are prone to reinvent the wheel. People, there's a lack of research focus. So as much as you're trying to push the frontier on a certain place from a certain angle, you're also forced to do other certain things, like things like the data as well as algorithm focus. What I'm trying to say is the lack of research, this lack of standard benchmarks leads to lack of research focus. So as opposed to an ideal situation where people would either be certain groups would be focused on pursuing the improving the algorithm, and some other group would focus on improving the data encoding representation. When you work in this space, you tend to do both of them at the same time, which in some cases would not really enable sufficient progress in this particular direction. And then there's a distorted view of progress, because some other person could come up and be like, oh, this is my work, but then it's an essentially data scope, essentially different data scope, different domain was used, essentially different features was considered, and then it's very hard to objectively measure progress. And then this also impacts the trust and safety of these models. And then I will recap the main points. That are street shapers in many ways. They affect how we live our lives, affect the kind of opportunities that are present to us. And I also talked about how machine learning has potential for street networks, especially from the point of view of of improving accessibility, from the point of view of reducing costs, and as we move towards an equitable future society, or the democratization of society, machine learning has a potential to improve, to further that agenda. But then data modeling and standardization are the biggest challenges that that is being faced in the field at the moment. And we've made some efforts to address some of this, particularly from the point of view of transfer learning, representations, and graph neural nets. And as we even though we've made this efforts, we still feel like there's a lot that needs to be done. There's a lot of work, there's a lot of potential, there's a lot of exciting directions to explore that still remain. And we're hopeful for the future and hopeful that things improve, and that we keep on making progress as we go. And that concludes the talk. And I think that's it. If anyone has any questions, I am happy to take them now. So these are the references for the papers and that I talked about. And yeah, cool. Thanks.
Wonderful. Thank you so much for this talk. I'm going to end the live stream and the recording, and then people can maybe ask a bunch of questions.
Okay.